This is our fourth video on acid-base chemistry, and here we're going to talk about titration curves. Right, so what's a titration curve? First of all, it's a graph of pH versus volume as you add your titrant. So in other words, as you do the titration, you're going to monitor the pH and make a graph, ultimately make a graph of pH versus volume. So let's first talk about titrating a strong acid with the strong base. And this is going to be the easiest case because you don't have to deal with strong acids are 100% dissociated, and you don't have to deal with any equilibrium. So in this example, let's generate a titration curve for the titration of 25 mils of 2/10 molar with 2/10 molar hydrochloric acid with 2/10 molar sodium hydroxide. Right, so we're going to first calculate the initial pH. Okay, so you know that hydrochloric acid is a strong acid, meaning that it's 100% dissociated, right? So what's the concentration of hydronium ion in 2/10 molar hydrochloric acid? It's simply 2/10 molar. So we take the negative log of that to calculate the pH, and you get negative log of 0.20 and you get 0.7. Alright, so that's your initial pH. Okay. Second, let's calculate the pH after the addition of 10 mils of the sodium hydroxide. Okay, so let me write out the reaction for this. So you should be able to do this already, but I'll write it out anyway. So hydrochloric acid plus NaOH, sodium hydroxide, makes salt plus water, right? So basically, as we do the reaction, HCl concentration is going to go down. Anyway, so what's going to be the pH after the addition of 10 mils of the sodium hydroxide solution? So we're going to have to first figure out how many moles of HCl we started with. Okay, so we started with the HCl had a concentration of 0.20 molar, and we started with 25 mils. Okay, so 25 mils. Now you remember that big M. What does that stand for? That's a concentration unit. That's molarity. That's moles per liter. So 0.20 moles per liter. So to be consistent with the units, milliliters had to be converted into liters. That's how 25 became 0.025 divided by 1,000. All right. So 0.025 liters times 0.20 moles per liter is 0.0050 moles, or 5 times 10 to the minus third if you wish. Alright. Now, how many moles of sodium hydroxide have we added? Okay, we added 10, they were the same concentration, 2/10 molar, and we added 10 mils of the sodium hydroxide, so that's 0.010 liters times 0.2 moles per liter is 0.002 liters. Okay, so by how many moles of HCl did we lose? This number, 0.0020. So how many moles of HCl do we have left? 0.005 minus 0.002 is 0.0030. Now, we can't quite take the negative log of this to get our answer because that's moles. And pH is negative log of the hydronium ion concentration, so we have to divide this by the volume to convert it into a concentration. Okay, so what's our volume? Our new solution volume is 0.035 liters. Well, how did I get that? We started with 25 mils and we added of the acid, and we've added 10 mils of the base, so our new volume is 0.035 liters. Okay, so what's the concentration? 0.0030 moles divided by 0.035 liters is 0.086 molar, and so you take the negative log of that and you get a pH of 1.06. Okay. Now, so now let's calculate the pH after the addition of 25 mils of sodium hydroxide. Okay, now that's the equivalence point. So first of all, what's the equivalence point? The equivalence point is where we have added enough of our titrant, which is in this case the base, to completely react with all the acid. Okay, so how did I know this was the equivalence point? There's an easy answer to this. Go back and look at the problem. They were the same concentration. 2/10 molar and 2/10 molar sodium, 2/10 molar hydrochloric acid and 2/10 molar sodium hydroxide. So if we start with 25 mils of the hydrochloric acid, how much base is it going to take to reach the equivalence point? 25 mils. So that's how I know 25 mils is the equivalence point. Or we could calculate it out. Okay. Initial moles of HCl, we already did this calculation. In the previous example, we had 0.0050 moles of acid. How much base have we added? That same number. So basically, at this point, there is no more acid. What we have at this point is basically a solution of salt water. So the only hydronium and hydroxide ions come from the autoionization of water. Okay, so basically here we have a neutral solution, so there's no acid or base. The only hydronium and hydroxide come from the autoionization of water, so each is 1 times 10 to the minus 7th, and you have a pH of 7. Okay. Now, what's going to be the pH after the addition of 26 mils of the sodium hydroxide? Okay. So again, we figure out how many moles of HCl did we start with. We've done this twice before now. 0.0050. Okay. How many moles of sodium hydroxide have we added? 0.026 times 0.20 is 0.0052, right? So we've gone past the equivalence point. All the acid is reacted, and basically we have excess base. So how much excess base? Basically 0.0002 moles. Okay, now just like in the previous part, we can't just take the negative log of that to get the POH. Now it's going to, that represents hydroxide, so that's going to be, when we take the negative log of that, that's going to be the POH, but we can't just take the negative log of that because that's moles, and when you take the POH, it's negative log of concentration, so we have to divide that by the volume. So what's the volume? We started with 25 mils. We've added 26 mils. So the volume is now 51 mils, or 0.051 liters. So we divide moles by liters to get the concentration, and you get 0.0039 molar. Okay, now take the negative log of that. Just keep in mind that represents hydroxide, because we've gone past the equivalence point. When you take the negative log of that, that's 0.0039, which is 2.41. Now, one more time, that's the POH. So to get the pH, we have to subtract that from 14, and you get 11.59 as your pH. Now, when you titrate a strong acid with a strong base, if we were to make a graph here, okay, of pH versus volume, we would get a graph that looks like this. Alright, so you get this S-shaped curve. But there's a couple of features about this that are important. Okay, number one is that this curve is symmetrical. Okay, when you titrate a strong acid with a strong base, the curve is symmetrical. The second thing is the pH is 7 at the equivalence point. Because when you're at the equivalence point, you've added enough base to react with all the acid. The resulting solution is neither acidic nor basic. So your pH is 7 at the equivalence point. Okay? And then a third thing that I want you to notice true, and to notice also, that initially the change in pH is pretty small. When we first start out, there's not a huge change in pH. In the first part of the problem, we went from initial pH of 0.7 to 1.06, which is not that much of a change, but the higher up you go, further along you go, as you get closer to the equivalence point, then there's big changes in pH. Okay, now let's do this again. We're going to do this again. Let's go through these calculations again, except now we're going to titrate a weak acid. Okay, this is going to be a little bit different. Okay, so let's say we want to generate a titration curve for the titration of 30 mils of 2/10 molar acetic acid with 2/10 molar sodium hydroxide, right? So again, they're the same concentration, which sort of simplifies things a little bit. Okay. So we're starting with 30 mils of 2/10 molar acetic acid. Okay? So first thing is calculate the initial pH. Now, you ought to be able to do this in your sleep at this point. We went through a separate video on how you calculate the pH of weak acid, weak base, and so forth. The equation that you have to solve comes down to x squared over the concentration is equal to the K. Hey, this number is probably burned in your brain at this point because I've used acetic acid as for so many examples. Ka for acetic acid is 1.8 to the minus fifth. So cross multiply 1.8 to the minus fifth times 0.2, take the square root, you get 1.9 times 10 to the minus third. Take the negative log of that to get the pH, and your pH comes out to be 2.7. Right? So this is the first difference. This is the first difference titrating weak acid versus a strong acid. Right? The initial pH is higher because it's not 100% ionized. Our 2/10 molar HCl had an initial pH of 0.7. So this is higher. Okay, now, alright, so second part is let's calculate the pH after the addition of 15 mils of sodium hydroxide. Now, this is important. And I'm going to show you how to do it the long way, but there's also an easy answer to this because this represents the half equivalence point. In other words, you've neutralized half the acid. How did I know this? Because they're the same concentration, and we started with 30 mils of acid. So it takes 15 mils of the base to get to the half equivalence point, right? So we'll see why this is important. So your initial moles of acetic acid will be 30 mils is 0.030 liters times 2/10 of a mole per liter. That is 0.00 0.60 moles. Okay. So how many moles of sodium hydroxide have we added? 0.15 mils, stated in the problem, which is 0.015 liters times 0.2 of a mole per liter is 0.0030 moles. Okay, so we definitely have not added enough base to react with all the acid. We've added enough to react with half the acid. Okay, so how many moles of acid do we have left? 0.0060 minus 0.0030 is 0.0030. Now, to get the pH, we have to convert those into a concentration, so we divide by the volume. Well, what's the volume? We started with 30 mils, we added 15, that's how I got 45 mils, which is 0.05 liters. You divide, that's 0.067 molar. Now, let's think about this for a minute. What have we basically done here? What we did was we made a buffer. Okay, remember, a buffer is able to resist changes in pH because it has an acid and the conjugate base of the acid. Let me write the reaction out here. So when we write acetic acid plus sodium hydroxide, what does that make? It makes sodium acetate. I'll just write it like this: acetate plus sodium ion plus water. So as you titrate, you're converting acetic acid into acetate. So up to the point where you get to the equivalence point, and we're not there yet, you have a mixture of acid and conjugate base. That's a buffer. So basically, so as you titrate, you're making a buffer. Now you ought to be able to see what's special about the half equivalence point. How do you calculate the pH of a buffer? Henderson-Hasselbalch equation, 4.74 plus the log of the ratio of the ions. Well, at the half equivalence point, those two ions have the same concentration. Okay, 0.030, 0.0030 divided by 0.0030 is 1. And the log of 1 is 0. Okay, so basically then the pH comes out to be 4.74. Or we could say at the half equivalence point, the pH is equal to the pKa. So if you to recognize this, and I wanted to work it out to show you why this is, but if you to recognize at the start that this is the half equivalence point, you don't even need to do all this. pH is pKa. Just take the negative log of the acid dissociation constant. Okay, the half equivalence point, the two are the same. Okay, so now let's calculate the pH after the addition of 30 mils of sodium hydroxide. Okay, so we're now at the equivalence point. Okay, so we started, they were the same concentration, 0.2 molar. We started with 30 mils of acid, and so we've added 30 mils of base so that there is no more acid. So what do we have now? Solution is now 10th molar, basically the solution is now 10th molar sodium acetate, right? Well, how did I know 10th molar? I kind of skipped a step there because the initial concentration was 0.2. If we started with 30 mils and we've added another 30 mils, then the initial concentrations are half what we started with. In other words, this concentration is half the concentration of the acid because we've gone from 30 mils to 60 mils. We started with 30 mils, we've added 30 more mils, so this concentration is half the concentration of the acid that we started with. So, as you know, sodium acetate is the conjugate base of acetic acid. The solution is going to be basic. because by converting the acid over, by adding the sodium hydroxide, we've converted the acid into the conjugate base form, right? This is, one more time, this is the conjugate base of acetic acid. So the solution is going to be basic. This is another difference between titrating a weak acid versus a strong acid, okay? When you titrate the strong acid, we add a pH of 7 at the equivalence point. That's not going to be the case here. pH is going to be higher because by titrating, we've converted the acid over to conjugate base form anyway. So what's the pertinent reaction now? The sodium acetate is the only chemical species in solution. We don't have any more acetic acid in solution. So what's our reaction? The acetate begins to react with the water and reform acetic acid. Okay, so basically then, this is how do you calculate the pH of 10th molar sodium acetate. This is a calculation we've done before. So you first calculate, we first calculate the Kb. So Ka times Kb is Kw. Rearrange this for Kb. We've done this before. Kb is Kw over Ka, which is 1 times 10 to the minus 14th divided by 1.8 to the minus 5th. It's 5.56 times 10 to the minus 10, right? So now, we could write it out. The reaction is going to shift to the right. We'll produce X moles of sodium acetate and X moles of hydroxide, or these will go up by X and that'll go down by X, but we'll neglect the effect of the dissociation and say that's 0.1. So the equation we'll have to solve comes down to X squared over 0.1 is equal to K. Cross multiply, take the square root, and X comes out to be 7.45 times 10 to the minus 6. Now, be careful, because X represents hydroxide. Okay, so when you take the negative log of that, you're getting the POH. So you take the negative log of that, and it comes out to be 5.12. Subtract that from 14, and your pH is 8.88. It was 7 when we titrated the HCl, right? So the pH is higher. pH is higher at the equivalence point than when we this pH is higher at the equivalence point than when we titrated the strong acid. So now let's do one more calculation. Okay, so let's calculate the pH after the addition of 35 mils of sodium hydroxide. So we've gone past the equivalence point. In fact, we've gone way past the equivalence point, like 5 mils past. Okay, so we'll do we're going to have to figure out how many moles of excess sodium hydroxide we've added. So how many moles of acid did we start with? The 30 mils, which is 0.030 liters, times 0.2 of a mole per liter is 0.0060 moles. And how many moles of sodium hydroxide have we added? 0.035 times 0.2 is 0.0070. Okay. How many moles of excess have we added? Subtract the two, 0.0010. Just remember that's moles. That's not molarity. It's not concentration. We have to divide that by the volume to convert it into a molarity. All right. So what's our new solution volume? We started with 30 mils. We've added 35 mils. So the new volume is 65 mils, which is 0.065 liters. You divide the moles by the concentration. That's 0.015 molars. 0.015 molar. Okay. So remember, this represents hydroxide. You take the negative log of that, you're getting the POH. That's 1.81. Subtract that from 14, and that's 12.19. So you might want to make the argument, but we also have some hydroxide coming from the previous reaction. In other words, the acetate reacting with water, but that is negligible compared to having a huge amount of excess sodium hydroxide added. So you really don't have to worry about that here at the end step. Alright. So when you titrate, let's recap this. When you titrate a weak acid with a strong base, what's the difference? Okay. The initial pH is higher. Okay. The initial pH is higher. When as you titrate, you're making a buffer, and when you reach the half equivalence point, pH is the pKa. Your pH at the equivalence point is going to be higher. It's going to be greater than 7, because by titrating, you're converting the acid into conjugate base. Let's write these down. So what do you have? Initial pH is higher. Okay. At the half equivalence point, the pH is equal to the pKa, which is an easy calculation if you know to look for that trick. Okay. And your equivalence point, your pH at the equivalence point, is going to be greater than 7. Because in the course of the titration, what you've done is make the conjugate base of the weak acid. And that's it for titration curves. We'll stop here.